So in the previous video, we introduced confidence intervals. However, how do we construct these confidence intervals in practice? Let me show you how with a hands-on coding example here.
So for this video, we are going to assume we already pre-trained our large language model, and now we are interested in constructing confidence intervals for the test set accuracy. So here I have a model from Unit 8 and 9, the Distilled model, that we trained on the movie review dataset. So that's the same code here, and I'm not walking through this because we already discussed that several times. The interesting part though is at the bottom, the test set accuracy. So this model achieved a 91.79% test set accuracy, and now we are going to add a confidence interval for this test set accuracy. And I should say there are many different types of confidence interval methods. So there is method 1, the normal approximation interval based on the test set. There is also method bootstrapping the training sets, where it doesn't require a test set. Method 3 is bootstrapping the test set predictions, and method 4 is constructing confidence intervals from retraining models using different random seeds. So each time we change the random seed, the model will be slightly different. So these are all different valid methods for constructing confidence intervals. Some of them at least, they measure I would say different aspects. We are not going to go into too much detail here because it's Unit 10, the conclusion of this class, and this would be almost a class on its own. But if you are interested in further details, I have an article here, Creating Confidence Intervals for Machine Learning Classifiers. And I've also written an extensive article here, which you can find on Archive, where it explains a bit more the theory behind it. So for simplicity, we will take the first method here, the normal approximation interval based on the test set. And based on my experiments, it's also pretty much consistent with the other methods. So they all, to certain extent, agree with each other. So you can find out more details here. But of course, let's say different contexts may require different methods. But let's maybe not get distracted here. This is a very common method. I would say it's maybe the most common method for constructing confidence intervals. So it's in any way useful to learn about it. So it's not only the most popular method, I would say, it's also among the easiest way of creating confidence intervals. And how it works is that we are essentially computing a confidence interval from a single training and test split. So we don't have to, let's say, apply our model to multiple data sets, because that's usually a limitation that we have in practice. And it's particularly attractive in practice because the model training is expensive. So if we only have to train the model once and apply it to one test set, then it's cheaper in the context of deep learning, where it takes sometimes many days or weeks to train a model. And it's also attractive because it evaluates this specific model. So some methods, for example, they require you to retrain different models, and then the confidence interval would not correspond to a particular method or model. So it would be more like including all the different models that were trained on the, let's say, different k-fold cross-validation faults or bootstrap samples. So here we are really evaluating a specific model that we might or might not employ in practice then. So how does this method work in a nutshell? So assuming that we have a normal distribution, and by the way, if you are not familiar with, let's say, statistical distributions, don't worry about it too much. I will also provide you with, let's say, more resources, or maybe the best way would be to reach out via Discord or the GitHub discussion page, and I'm more than happy to share more resources with you. But if you are familiar with, let's say, distributions, so here this method works by assuming that we have a normal distribution, and then for a parameter like the accuracy, we can then compute the confidence interval as follows. So we take the accuracy, and then we have plus minus z times the standard error of the parameter. So z is essentially how many standard deviations the parameter lies away from the mean of the standard normal distribution. So I should have maybe included a figure, but if you have a standard normal distribution, you can essentially divide the plot, this Gaussian bell curve, into, let's say, sections by using a standard deviation. So z basically is a measure of how far you are away from the center of this curve. And the standard error here is essentially the standard error of the parameter that we are interested in. And I will show you at the bottom how we compute it. So this makes another assumption. So here we are modeling this in the context of a binomial proportion confidence interval. And again, this is, I would say, a bit tricky in terms of if you are not that familiar with distributions. But I have a more, I would say, step-by-step explanation of that in my article that I referenced above. So I've written about this in more detail here. So this, like I said, would be almost a lecture on its own. So maybe for this example, just assume that this is correct and we can make this, let's say, approximation, this binomial proportion approximation or assumption. And then we have the following formula here where you have the standard error as the square root of 1 over n, where n is the test set size. So in our case, the movie review data set has 10,000 data points. So we would divide or normalize by 10,000 here. And then we have the accuracy times 1 minus the tested accuracy again. And this standard error is then plugged into this value here. So we have z times the standard error. So how do we get z? So this is usually, I'm not sure if you've done that, but if you've taken a statistics class, you might remember like t-tables. So this would be, in this case, a z-table, which is almost the same thing where you can look up this value from a table that someone tabulated. So if we are interested in a 95% confidence interval, we would look up where, let's say, 95% of the data falls under the curve and what standard deviation or z-value it would correspond to. So this is very complicated, like looking things up in tables and so forth. So I will just show you the, let's say, easier way using SciPy. So using SciPy, there is a formula where we can compute the exact z-value that we need for a, let's say, 95% confidence interval. So here we have the confidence level that we want. 95% is a very common one, maybe the most common one. So we are going here with 95%. Like I explained in the lecture, this would then correspond to the 95% confidence interval we are constructing. So then we compute the z-value here using this SciPy function and plugging in the value. And the normal distribution, it has two tails essentially on the left-hand side and the right-hand side. And we are interested in a 95% around the mean. So we are essentially dividing by 2 because we have 2 endpoints here. So we have 1 plus the confidence interval divided by 2 here to get the correct z-value. So in this case, this would be 1.959, so about 1.96. So this z-value, if we have a curve, a bell curve, it would be 1.96 standard deviations from the left-hand side and 1.96 standard deviations from the right-hand side, so that we capture 95% of the data distributed around that mean, essentially. So if we have this value, we can then compute the confidence interval like shown here, where we plug in the z, so the 1.96 times the standard error. The standard error we have to compute. So for that we need n, which is the length of the test set. So let's do len test dataset. I should have defined it above because I ran this in a separate section. I may have to actually run this, but I can just tell you this is 10,000. So if I would scroll up, let me search for test dataset here. So if we have this one, the length of that should be 10,000. Let me just run everything up to this cell here and then including the cell. So if we have this, we can then double check, then test dataset. And this is 10,000. So let's get back to our confidence intervals here. So we have n is 10,000. And the test set accuracy that we need, let's say x test, this we can get from up here. So this would be our test set accuracy. And then we can compute the standard error here. We can do this actually as follows, where we have SE equals square root of the accuracy test times 1 minus the accuracy test divided by n. And then we can compute the confidence interval length as CI length equals the z-value that we have here times the standard error. And then it's plus minus. So what we do is essentially we have accuracy minus this length of the confidence interval, and accuracy plus the length of the confidence interval. So this confidence interval is symmetric. So the left and the right hand side, or the lower and the upper part, will be identical. So let's print out these values and see what they are. So our 95% confidence interval for the test set accuracy here is 91.2%, the lower value, and 92.3% for the upper value. So this would be our 95% confidence interval. So let's also visualize this in a plot. So I'm just pasting the code here. So we use matplotlib, create a new figure, and then we use this error bar plotting function where we can provide the test set accuracy and then the confidence interval length, which is essentially then doing what we have done here manually. And this is just the annotation for the plot, and this will then plot the confidence interval in a plot here where this is our accuracy value at 91.7%, and then we can see the lower and upper confidence interval. And in practice, we usually do that for different models when we want to compare different models. So here we only have one model, but you can imagine if you have multiple models, you would put them side by side and then visualize the performance of these models with confidence intervals. And so this is how it works in a nutshell.
So in this video, I talked about different ways we can use to construct confidence intervals, and you have seen a hands-on example. So I hope this will be useful for you in practice when you compute the accuracy of your models.